All right, so we're going to talk about electric fields. So fundamentally, the base concept of an electric field is that every charged particle creates an electric field. Which I'll just usually call them E fields. All right, now that's great, fun facts. But the thing is, well, okay, what's it look like? Why does it look like it? Things like that, because we can't see them. All right, electric fields are like gravitational fields, they're just there. So we define an electric field by the net force acting on a positively charged, massless, we call them test charges. So it's really a hypothetical thing. It's not a real thing. You don't actually put a physical charge there. You conceptually put a charge there. All right. So if we look at, say, a positively charged sphere, if we were to put a test charge, say here, it would be pushed away. And the farther we got, that would get weaker and weaker. So we basically have these field lines that look like they go out like yay. All right. So the closer we are, the stronger. And the farther we are, the weaker we are. All right. So close gives strong fields, weak gives far fields. Why? Good question. Glad you asked. Well, that would be because of Coulomb's law. All right. We know that Coulomb's law is KQQ over R squared. So the closer we are, the stronger it is exponentially. And the farther away we are, the weaker it is exponentially. So that's one thing. Second thing, I'm going to bust out some colors here. All field lines point in POINT. Oh no, that can't stand. We got to erase that. Bloop. POINT. All right. In the direction of the force. And we know that likes repel, likes repel, and opposites attract. So in this case, it's a positive. And since these are all positive test charges, then we know that they're going to repel. So we're going to get lines that all go away from it. So I can do more and more lines like so. And we can see that as we evaluate these lines, we said, okay, so the farther away we get, the weaker that field is. And that makes sense. If we look at the distance between the lines, I'm dropping layers today. So the distance between the lines tells us the strength of the field. So here we can see that as we move farther and farther away, the spacing between the lines gets bigger than before, and it'll just keep getting bigger. And so the strength of the field gets weaker and weaker and weaker as we get farther and farther away. All right. So tighter lines, stronger it is. So close lines have a more dense field, just for density, and the farther away we are, they have a weaker density. All right, so that's the basics. So now let's basically apply it to a few situations and see what we come up with. So first basic situation is we'll have a positive and a negative charge, And we want to know, okay, what's the field look like if they interact with each other? Well, positive, they go away, and negative, they go towards, because it would attract. But they're going to interact with each other. So let's say we are a charge out here. We are going to feel a push this way, and we're going to feel a pull, but that pull is going to be weaker. So my resulting field of force, which tells the field, will be that. If I then go to, say, the halfway points, let's say it was somewhere here, then it would feel an equal push and an equal pull. So we would have a line like this. You can probably see where I'm going with this, but I'll do one more just for fun. And so if we were, say, down here, we'd feel a big pull towards and a weak push away. So it's a very strong field line like that. So we basically get that's kind of what I want. So it'll arc. Okay, so we'll get these arcs that go around. And we'll have these big bulges here because the lines are going to get, the strength of the field is going to get weaker as we get further away. In the middle, we're just going to have one line going straight to. These will all have arrowheads on them, showing the directionality of the field. And if it was on the absolute ends here, it would go away and then towards. And obviously this will just repeat itself out here. How many lines you want to draw, that's up to you. But yeah, looks kind of like a spider, I guess. I don't know. But that would be two positives. I'm sorry, positive and negative. I'm having a day today. All right, let's do another scenario. So what if they don't have the same charge? So let's say we've got a singular charge, and then we have one that has 3 times that charge. All right. So this is going to have 3 times the charge. Oop. And because it's like a +1 versus a +3. Now, these are both positive, so they're going to push away from each other. Now, when they get to here in the dead middle, there's going to be some point where we have absolutely no net force because they'll balance out. If they were equally charged, that would be in the dead center. But since this one on the right has a greater charge, it has the ability to apply a greater force. So we'll probably have our dead zone somewhere about there. All right. So that means that there's going to be this point, this asymptote right through that line where our field will always equal 0. And because of that, our field lines look very interesting. So we have them pushing up and away like so. They'll go to that asymptote, which is the line of 0 net force, aka no net charge. That should not have been a straight line. All right, but they will go away. And this will go away, and will look like this, and will look like this, and so forth, and so forth. All right. Now, besides this is the reaction between two positives, it'll look totally different than opposite charges. So 2 negatives would create the same thing, just the lines would be going in instead of out. But it shifted over because this has 3 times the charge of that one. So if there's an imbalance, there will be a shift in your asymptote, which is the location of 0 net force. But also, this one has a stronger charge. So that means that we are going to have a greater density. So we should have extra lines here because the field is stronger because we have extra charge. So it would look more like this, which then it makes sense why it's pushed to the left because we have way more fields. It's like having way more lines. We're just going to push back on fewer things. Just draw a few more lines. All right. So that would be those. Now, these are singular charges out in space, no problems. It's good conceptually. This is not what we actually would deal with in the scientific field. I mean, we can evaluate it, but it's really rough because the field is constantly changing. You'd have to use a computer simulation to actually evaluate what's going on because as one moves, everything else starts moving, the field keeps changing, things like that. It's pretty ugly to deal with. But we can do like at a moment in time, no problem. What we actually use for moving particles is we use something that's kind of like this, two parallel plates. If you're really old or just have old stuff, this is how the old TVs used to work when they had the big tube TVs. If you have no idea what I'm talking about, ask your parents. Maybe they know, maybe they won't. I'm getting old. What can I say? But you'd have the big glass TVs and they'd have a tube in the back and it made a buzzing sound. It wasn't cool. But the interesting thing about it is you'd fire off electrons. The electrons will move around based on how they interact with the field. Now here the field is very nice because it goes away from the positive towards the negative, away from the positive towards the negative, repeat, repeat, repeat. Now on the ends, we've got our arcs. So, it would go around like this and so forth. And I could keep drawing all the way in the middle here. But the interesting part is the middle, because if we have this uniform field and we were to, say, fire an electron through it, we could evaluate what's happening to it, and it would behave very similar to it would behave very similar as to a projectile. So if we had an electron, I got the colored thing going on. Why not? And we had an electron and we fire it through this field. The electron will be pushed away from the negative and drawn towards the positive. So the electron will go like this and it'll bend around. So it's good uses. We used to do that. We'd fire the electrons out of this and then they would curve and they would end up hitting the TV screen at certain points, and that would light up the TV screen so you could see it. And that's why if you ever watch an old movie and they've got an old computer screen in it, you'd actually see a line slowly going down the screen, because that's the interference pattern between the camera taking images and the rate at which the electrons are being fired at the screen. Totally not on any test, but fun fact. So this is what you need to know for electric fields. Up here we have the core concepts. Down here we have a few more elaborate examples of their applications. All right, that is all I have for you today. You guys have a blast, and it's been fun. I'll see you next time in physics class.